in the right order. So first of all, just to mention, this is a joint effort between the IA Energy Storage Task 36, the UK Super Energy Storage Network Plus, and the University of Birmingham Center for Energy Storage. So we have a fantastic agenda for you, which I would like to essentially remind to you. I just drop in the chat again the link to the agenda if you want to refresh who the speakers are. So we have a mix of talks from academics and from industrial experts on Carnot batteries, and obviously there will be opportunities for you to ask questions. So you can do this in two ways. So you can drop your question at the bottom of the Zoom facilities in the chat box, or alternatively, if times allow, you can raise your hand and unmute yourself so you can ask directly your question to the speaker. So one thing I need to tell you, as you might notice, that Angela is recording this webinar. So we very much hope we can take for granted the permission to do so. So if that's not the case, please contact Angela afterwards, and so we can discuss what parts need to be omitted eventually. So I would like now to bring in Dan Bauer from DLR Germany, who is leading the IA Task 36 on Carnot batteries, and he will tell you more about the task itself. So Dan, if you are there, you are welcome to join and to share your screen.
Yeah, thank you very much, Adriano. I'm going to share my screen. So very welcome everybody also from my side. My name is Dan Bauer from the German Aerospace Center DLR. I'm here as the task manager of Task 36, which is a working group on Carnot batteries in the framework of the International Energy Agency's Energy Storage Technology Collaboration Program. And as you can see, it is a group consisting out of like 40, 50, 60 participants from industry, from academia, so from research centers and universities as well. And they meet to bring the topic Carnot batteries one step further. For those of you who are not familiar with Carnot batteries, I want to introduce the Carnot battery as a technology. Carnot batteries are not a new but an emerging technology, and they are meant for the inexpensive and site-independent storage of electric energy at medium to large scale. And this is done by transforming electricity into thermal energy through a kind of a conversion technology that can be a heat pump, or it can be a resisting heating or something else, kind of a compressing technology. Then storing this thermal energy in inexpensive storage media that can be water, that can be molten salt, rocks, and some other things like even liquid air. And in a third step, this thermal energy is then transformed back to electricity when electricity is required. So such a Carnot battery consists out of three parts: a conversion system from electricity to thermal energy, a thermal energy storage system, and as a third part, the reconversion system from thermal energy back to electricity. And it's basically meant for the storage of electric energy. In addition, it can be a tool for power and heat energy management by either consuming thermal energy during the charging phase. This can be done when the conversion system on the left side shown here is a heat pump, and by producing combined heat and power during discharging. So the basic idea is electricity storage, but one more benefit can be that it can be used as a tool for power and for heat management. We structured this working group, Task 36, into several parts, into several subtasks. subtask 0 is kind of a starting point for the whole task. It's kind of a baseline giving subtask working on definitions, working on the classification of Carnot batteries, working on the definition of key performance indicators, and so on. Then we have a scientifically oriented part consisting out of subtask A, B, and C, and they work on different Carnot battery technologies, Rankine-based, Brighton-based, or other concepts and combinations of different kind of Carnot batteries. And then there's a subtask D, which is a market and policy oriented subtask. This task 36 will run for 3 years. We are at the beginning of the 2nd year, and there are, of course, some planned outcomes that we are working on. First one is standardization. So we are defining acronyms, we are defining key performance indicators, giving reference cases, and so on. Second planned outcome is data collection and management through project databases, through fact sheets that we are collecting and later providing, through best practice databases, and so on. And in the end, we hope that we are able to even provide a CAPEX, OPEX, or levelized cost of storage database. Third planned outcome is communication and information through workshops, webinars like this one right now, through Wikipedia page. There's a first version of the Wikipedia page on Carnot batteries already existing, through other roadmaps, and so on. And then next outcome is kind of an outlook. We are planning to give some kind of research and development roadmap at the end, and also a market map. Altogether, you can say that the planned outcome is to collect and to provide information for all stakeholders, and through this, bring the technology one step further. Not to forget the last outcome. This is to establish an international platform that brings together experts from industry and academia in a structured way, to provide them a platform that they can meet, where they can exchange. It consists at the moment out of more than 100 participants that have registered, and 50 to 60 out of them are regularly participating in the meetings. They come from 46 institutions worldwide, from 14 countries at the moment. And if anybody is interested in participating as well, or just want to have more information on this task 36, please have a look at this homepage shown here. It's iea-eces.org/annex-36. That's from my side for the beginning. So welcome again, everybody. I wish you a very fruitful and interesting webinar, and want to hand over to Professor Yulong Ding, who is doing the welcome on behalf of the UK Supergen Energy Storage Network. Yulong, please. Yulong, you need to switch on your...
Thank you very much, Dan. Thank you, Adriano. And first of all, very welcome to fairly sunny Birmingham, although you can only see virtually from my background, but slightly cloudy. And then we were wanted to have everybody to be in Birmingham physically, but we couldn't do so. And this webinar provides such an opportunity to bring academia and industry together to discuss some key areas of Carnot Battery initiative and technologies. And so I would like to thank you on behalf of UK Supergen Energy Storage Network, which I'm leading, and also Birmingham Center for Energy Storage, for which I'm leading as well. So I wouldn't say too much, but I think the key things today really is to look at key challenges for Carnot Battery technology, particularly from component level, because there are some challenges for some specific conditions. And we would love to understand a lot more about the performance, the potential for the future Carnot batteries. And with that, I think I'm going to pass on to Angela. And before I do so, and I do hope you all enjoy the meeting today, and hope you we can sort of bring this technology to the next step. And also this year is the COP26 year, and hope we can have something to show in one way or another to the world that net zero future is the future. It's not sort of a dream, although it's difficult, but I think hopefully that would sort of bring everybody on board toward that vision for the future, for our the globe, for our world, for the Earth. So I'll pass on to Angela. Thank you very much.
Hello everyone, and welcome from me too. I'm here as my role as a project manager for the Super Energy Storage Network Plus, and I want to give you a very brief introduction on who we are and what we do. So the Birmingham Centre for Energy Storage is a cross-school centre which convenes researchers from across the University of Birmingham, mainly to drive innovation from the laboratory to market. It was established in 2013 with a 12 million investment from UK industry and the EPSRC. So the centre has two interrelated components of cryogenic energy storage and thermal energy storage. The original planned research focused on novel thermal energy storage materials, their components and devices, system integration and optimization, techno-economics and policy analysis, and storage applications. So the centre has grown significantly over the past 7 years, and now its original research themes have been expanded to include cold chain technologies, electrochemical and electrical conversion storage, smart energy system technologies. We also have been doing work on thermal energy-based temperature regulation technologies, specifically for electrical vehicles. The centre also looks into manufacturing technologies, data science, and knowledge transfer. So we are a very strong team with 5 lead academics from multidisciplinary areas. As a centre, we are currently involved in over 30 research projects with a combined value of 50 million. We have research facilities and offices in Bay Labs, in chemical engineering, materials building, and the Fry building in the University of Birmingham. And from June 2021, we will have offices, labs, and incubator at Tyseley Energy Park. So if you want to see more about what kind of research we're doing, please have a look at our website. So I will also want to give you a very quick introduction about the Super Energy Storage Network Plus. So the Centre, University of Birmingham, and Professor Yulong Ding are leading the network, along with the support of 19 academics from 12 institutions. We have 1.2 million total in funding, with 1 million coming from EPSRC. From that, 450,000 is dedicated for our flexible funding activities. We have an additional 100,000 available from the International Energy Storage Alliance for joining the national projects. We have also very strong industrial support, with 2 million in kind support from 34 project partners. The duration of the network is 48 months, and the start date was September 2019. So our vision is to connect and serve stakeholders across the whole energy community, advancing and championing UK energy storage research and deployment. So we have several objectives that will help us achieve our main vision. Firstly, a detailed mapping of the whole storage community, which will help us understand, visualize, and integrate the whole community across disciplines and sectors. Another objective is to identify key research areas and the development of a white paper to steer future energy storage research. We also have to deliver a flexible funding scheme to address key research questions. A very important aspect of our network is to support early career research talent and expertise, and to set ambitious measurable goals for equality, diversity, and inclusion. So our long-term objective is to become a focal point for the energy storage community and associated stakeholders, and to deliver impact nationally and internationally. As you can see, we have launched 6 dedicated work packages, which are operating in parallel, each one addressing one single objective. So thank you very much for your attention. Please feel free to follow us on Twitter, look at our website, and see how we can work together in the future. Thank you very much.
Thank you very much, Angela and Dan and Yulong, for the very useful introduction. We are spot on time. That's great. So I think we can now dive into the talks. So we have the first talk from BASE, and the talk will be delivered by Choi Lianos on net zero innovation. So I believe if Angela, you can share the presentation so that Lianos can go through the talk.
Thank you. Thanks, Angela. Sorry, everyone. My technology doesn't allow me to share my screen in the same way, but we will get there joint together. Really great to be invited here to have this discussion. I'm Chloe Lianos. I sit in the UK Department for Business, Energy and Industrial Strategy, and specifically our Science and Innovation for Climate and Energy Directorate, where I lead our energy storage innovation agenda. I conduct a variety of different programs and competitions and research on energy storage innovation alongside other smart energy innovations to facilitate the decarbonisation of our energy system. We are aiming to accelerate disruptive technologies. We do look at the mid-TRLs, so the mid-technology readiness levels and above, but we work closely with our UKRI colleagues to understand what's coming up through the earlier TRLs too. And I'm also the UK delegate to the IEA's Energy Storage TCP, which this task is coming through. Next slide, please. So today I'm just going to talk to you about why we have net zero within focus and why energy storage within that. Energy storage and net zero feeds into a variety of different Her Majesty's government strategies. Here are just some of them. We have the Road to Zero, which is embedded in the industrial strategy. We've got our Smart Systems and Flexibility Plan that was published in 2017, which included actions specifically on storage. And that was also updated in 2018. And we are due to provide a new iteration of that shortly too. We've got our Clean Growth Strategy, but then most importantly, the recent publication of the Energy White Paper. This all sits under and informs how we're going to achieve our target of net zero by 2050. We set this in June 2019, and we have to deliver against it. So next slide, please. I'm going to talk to the Net Zero Challenge. I'm not going to go into it too much because we should all be familiar here on it. However, I wanted to give a bit of a depiction of the UK's greenhouse gas emissions and challenge ahead of us. As you can see on the left-hand side, there's a graphic of all the different sectors that we're mapping against. And you can see we've done a lot in the energy supply area. However, there's more to be done, for example, in the transport area. Energy storage sits underneath quite a few of these areas. It has an impact within energy supply, transport, business, and residential, and could actually feed into waste management too. So there's a lot to be done. Next slide, please. I just wanted to use this slide quickly to illustrate how far-reaching it is, as I alluded to previously, how we have all these different areas of work that we're looking at to combat, but to address our net zero commitment. I've highlighted in the middle the power area, where you can see we discussed the Energy White Paper, our ambition to be a clean wind energy world leader, our various different projects in the Contracts of Difference, and as well our specific new statement about more than 100 million of innovation funding towards energy storage and flexibility innovation challenges. However, energy storage, once again, can go through a lot of these different themes and contribute to achieving net zero across these different sectors. perhaps at a stretch, land use and greenhouse gas removal specifically, but I do think that it has a role to play across the majority of the areas. Next slide, please. Recently, at the end of last year, we had actually a statement by our Prime Minister about a green industrial revolution, and he set out his 10-point plan. This is providing action towards the words words that we intend to address net zero with. I'll talk to the 10 points quickly now. If we could go to the next slide. Here's a really brief summary, a bullet list of what those 10 points are. We have point 1, advancing offshore wind, and storage will facilitate that. We've got hydrogen, where some could argue storage could be brought into that as well. It's large case for storing hydrogen for longer duration. Point 3, nuclear power. There's been some discussion about storage being embedded with nuclear power too. There's, of course, energy infrastructure required for point 4's shift to zero emission vehicles. I could go on throughout all of these, but I think you get what I'm saying, that energy storage does fit into the majority of these. But the specific area that I'm looking towards and delivering this energy storage innovation across is within point 10. Next slide, please. Point 10 is the commitment to provide green finance and innovation. We are looking as a country to unleash innovation and develop new sources of finance. And specifically, there was a commitment to launching the 1 billion net zero innovation portfolio. This is a portfolio of work building off our existing energy innovation work, and will further aim to accelerate the commercialization of decarbonisation technologies. It has 10 priority areas. There's a theme here, lots of 10s within our net zero innovation portfolio. So I'll speak to those now. Next slide, please. This is, as I say, you can see the caveat at the bottom. It's a possible area, possible programs, but these are the 10 key areas that we will be looking at. It's an expansion of our existing energy innovation portfolio. It's going to be for over the next 5 years. We've been given £200 million specifically for this upcoming financial year to deliver against this. Once again, you can see that smart energy and energy storage is a key pillar of this. But again, we feed through to industry, to offshore wind, to hydrogen. There's a lot of crossover. Next slide, please. So drilling down into that energy storage innovation, within the 10-point plan commitment, we actually had a specific line on energy storage and flexibility innovation challenges. This wasn't done largely for the other 10 points, which again shows the political interest in this. We need longer duration storage. Well, we don't need, we think we need longer duration storage across days, weeks and months to help reduce the cost of meeting net zero by storing excess low carbon generation for longer periods of time, helping to manage variation in generation, such as extended periods of low wind. This will help reduce the amount of fossil fuels and low carbon generation that would otherwise be needed and optimize the output from renewables rather than paying to turn off the generators when there is excess supply. The commitment around this innovation point was further strengthened in the publication of the Energy White Paper, where we said that we would launch a major competition to accelerate the commercialization of first of a kind, longer duration energy storage. And this is part of our at least 100 million investment in storage and flexibility innovation. And you'll note that there's delivery from spring 2021. So this is what's keeping me busy at the moment. Next slide, please. Why are we looking at energy storage? I'm not going to go into too much detail on this. These are more for information. As you know, in order to achieve a flexible energy system that can deliver our net zero commitments, a whole system approach to decarbonisation of the grid is needed. In particular, the integration of increasingly higher levels of heat, transport and renewables into the existing power grid while maintaining system security and reliability and keeping the system costs low is one of the greatest challenges. And that's why we've got this policy supporting our innovation. This is just to depict on the right how flexibility is wider than just storage, but storage feeds into all of those areas. Next slide, please. Again, just a policy context map here for you to understand that we are constantly iterating our thinking, and we are always welcoming views to understand where you think we should be going next. This isn't a static publication of a paper. For us, we are constantly interested in understanding what more could be done and what are the challenges and barriers being faced. As I've said, there's going to be a new iteration of the Smart Systems and Flexibility Plan shortly. Next slide. I just wanted here to talk to what we see as the potential savings. Flexible technologies could save up to 40 billion to 2050. We see that system flexibility from storage, demand side response and internet connectors could actually have savings of around 6 billion per year in 2050, 6 to 12 billion, we've got it mapped there. And we currently only have 4 gigawatts of storage on the system. So there's lots to be done, because it's, as you can see, there's a potential modeling of 22 to 40 gigawatts. So we need to improve our pipeline at the moment, which we have about 6 gigawatts of battery storage and 3 gigawatts of pumped hydro storage. You'll notice that there's more emphasis on the shorter duration storage as well within our pipeline. So that again comes back to our innovation point of why we're looking at how do we facilitate longer duration storage to commercialize. Next slide, please. I just wanted to again show you the UK context of what we're using now for flexibility solutions, both from a storage perspective and a demand side response. You see here, I should apologise, these figures may not have been updated in the past couple of months, so they may be slightly out of date. I do caveat that. But it's just showing that there is a key part to play of storage assets within our markets for flexibility and the energy system. Next slide, please. So just capturing what I've said, there's a predicted modeled need for more energy storage to facilitate us to decarbonize our energy system and achieve net zero. What are we doing to facilitate this acceleration of energy storage innovation and deployment? Well, here on the right, there's examples of the work that we're looking at. We're looking at regulation, we're looking at revenues, we're looking at costs, we're looking at standards. But my specific area is the innovation spend area, where we're looking at cost reduction and developing our supply chain. And as I said, I work closely with UKRI to understand how that comes through. Next slide, please. So I wanted to just talk to you about our UK innovation landscape and actually just wider what's of interest, what bodies are interested in energy innovation, net zero innovation, and are delivering this energy innovation. Energy storage just feeds through all of these areas. Apologies to those coming from an international context, but perhaps this will be helpful to understand the UK landscape. I sit within that bracket called SICE in that second row, the Science and Innovation for Climate and Energy Directorate. And we have, as you can see, UKRI with us, where we worked through their arm's length bodies of Innovate UK and the research councils, which actually this is facilitated by the Supergen funded programme through EPSRC. We also highlight our knowledge bodies, Energy System Catapult and the Knowledge Transfer Network. Please do get in touch with them. They are great at networking and facilitating collaborations to be able to achieve our goals of net zero and really allow academia and industry and trials to collaborate and accelerate our net zero commitment, achieving our net zero commitment. Next slide, please. So I just wanted to talk quickly to what we've done so far. As I mentioned, our future, when I earlier spoke, I said we've got a future commitment of 1 billion, and this is building off our existing work. Well, this is our existing work. We have an energy innovation program that delivered across 6 different themes. Once again, you can see storage was part of these themes in the 70 million pot for smart systems. We are coming to a close of this program now. However, we do have some major achievements of this program, and that's part of the reason why we've been allocated further funding to continue the good work that we've got going. Next slide, please. These are just some of the major achievements to date from our Energy Innovation Programme. I've again highlighted the area that may be of most interest. However, Carnot Batteries may have applications in other areas too, such as the industrial brackets and the buildings, as well as the offshore, well, not just offshore wind, the renewables sector, the renewables theme that we're looking at. One thing that we do like to champion is our funding of the world's first cryogenic battery. That's a liquid air energy storage battery in Manchester to be delivered by Highview Power. We provided a £10 million grant to be able to deliver this. Other things that may be of interest are the £40 million Clean Growth Fund, which specifically targets early stage investment in clean tech. Also, we've provided 24 million for innovative projects to develop energy efficient homes by installing green tech and insulation in houses. Green tech also extends to storage in that context. Next slide, please. Let's go a bit into the storage area. This is just a really high level snapshot of what we've done with Energy Innovation Programme. We've delivered up to £30 million specifically on energy storage. This was through 3 different programs: energy storage cost reduction. I've included some of the technologies there. We looked at flow batteries, power to X, pumped hydro, copper zinc batteries, second life EV batteries. We then ran some feasibility studies, and then we had that storage at scale competition, which was what the Highview Power project was funded through. We also have our colleagues' areas of work that I wanted to highlight here: the Faraday Battery Challenge that you may be familiar with, as well as EPSRC's work, and our big variety of international programs too. Next slide, please. That was all in the past to the future. You've seen this slide. We're looking at what do we need to do from a smart energy and energy storage innovation perspective. I am wrapping up. Next slide, please. Once again, reminding you that we've got to focus on this longer duration aspect for now, but we are interested to understand what other areas may benefit from some of this innovation funding to achieve our net zero goals. Next slide. I'm wrapping up now. Where next? So we've got all these good plans. We've done all this good work. What's happening this year specifically? Well, we are looking to publish a series of sectoral strategies, which again, energy storage will have a part to play in delivering against. And then, of course, we've got COP26, as we've already referenced. Thank you. Final slide, please.
Fantastic. Thank you very much, Lianos, for your presentation. Very, very informative. So we have a few minutes, 8 minutes actually, for questions. So please drop your questions in the chat box, and I will read them aloud to the speaker. So we had a question before. Actually, I think when either Dan or Yulong were introducing the workshop as well. Do we plan to present at COP26? Perhaps, Lianos, you can say a few more words on your last slide and what BEIS plans to do there.
Sure, yeah. So the COP26 unit, delivery unit, sits between 2 government departments, Cabinet Office and BEIS, BEIS being the department I'm with, Business, Energy and Industrial Strategy. We are welcoming expressions of interest from partners who would like to present at COP26, so we do welcome that. I can provide further details of the email address to get in touch with. There is some published guidance as well on that. From a TCP perspective, an IEA TCP perspective, we are considering it across our delegates within BEIS, because we are members of a variety of different TCPs too. But I would be interested to hear if, yes, Yulong or someone else that was wanting to put their hat forward to present.
Thank you very much. Perhaps Yulong or Dan, any further plans for COP26?
Actually, I have a question for Chloe.
Go ahead, please.
It's about the base funding for the. Does this funding include batteries? You know, because we have a Faraday institution, and there looks quite separate from what might be allowed, you know, from your portfolio of storage aspects. If you could sort of clarify that, that'd be great.
It's a very good question, and something I should have been more explicit on. Thank you for drawing that out. I look at everything novel. So that actually excludes the more commercial solutions such as pumped hydro or now I'd say mature lithium ion technologies. The novel aspects of lithium ion are picked up by Faraday rather than myself. We want to ensure that we have funding across the board, and that's why we've got that distinction.
Do you mind a further question about industrial sector decarbonization, particularly heat? Sort of that is one of the focused aspects for decarbonization, about heating.
Sorry,
and cooling.
Sorry, you cut out there in the middle, so I wasn't sure if I got.
Sorry, the apologies. My internet is not good, so.
And mine.
So my question is about the heating and cooling decarbonization from base perspective. How important your view on that? Because we sometimes get slightly confused how, you know, because we know some of those we can do, some we can't do. Just the you know, for heating and cooling perspective, what sort of new initiatives you might perceive in the future? In the future, sorry.
So industrial applications are slightly out of my remit, but of course I stay on top of them because there is applications within energy storage. So I can't speak to the policy development there. However, I can speak to the innovation plans and funds that I'm aware of. So industry is going to be part of our net zero innovation portfolio. They are looking at plans and intentions now. So please do get in contact if you'd like to put your thoughts to my colleagues. I can make those connections there. So it will be one of the 10 priority areas within the net zero innovation portfolio. And then I'd also point you to the other funds, such as the Industrial Energy Transformation Fund. These are big challenge funds similar to Faraday, which will also capture aspects such as that. I've talked to the different strategies that are coming out. I'm not sure of the specific content, but I suspect there may be some references towards that there. But if there are concerns, please do let us know and I can pass those on to the relevant colleagues.
Thank you very much.
I'll put my email address in the chat again afterwards so that people can get in touch. Yeah.
Fantastic. So perhaps I'll take one more question in the chat, which referred to the long duration storage challenge was mentioned a few times. Is there a link or a specific place where we can go to get more details? And if I can add on that from my side, is there any, let's say, specific definition of what base intent consider longer duration storage? Is anything around that?
So first of all, further details. We are live in the process of trying to stand up that material now. We do intend to speak to it more publicly in the coming month. So do expect more details shortly. We don't have anything public right now, but we will be presenting something further in our initial round of market engagement, rather than launching the competition in its full in any way right now. With respect to your second question around what do we define as longer duration, we are technology agnostic, and we are driven really by our colleagues, our academics, our experts within the area. From my personal point of view, what we're looking at is the point where lithium ion falls off. So where does lithium ion not become competitive? Some say 6 hours, some say 4 hours. So we're looking at everything above that threshold. And so for us, we're really interested though in understanding how far can we go? We know that hydrogen may be touted as the solution for all of our longer duration storage requirements, but we're technology agnostic, and I'd like to understand the wider picture of other technologies available. And that's why tasks such as this are really important, because there may be a part to play, for example, from Carnot Batteries in this in the solution for longer duration storage. Apologies, we can't be more specific around what we mean, but again, that is one for my policy colleagues rather than me as an innovation delivery lead.
Fantastic. No, thank you very much. And yeah, hopefully these workshop helps to let's say define as well what we have beside lithium-ion batteries. Okay, thank you very much for your presentation, for the very useful information here. So I think again we are very much on time. And thank you again. I think we can move to the first presentation from industry. So the presentation is from Siemens Gamesa and is delivered by Maxwell Cameron Jones. We'll talk about the, let's say, technological development there at Siemens. Max, if you are there, please bring in or share your screen and go ahead with your presentation. Thank you very much.
Can you all see my screen now?
It's coming up. Yes.
Brilliant. So thank you very much for inviting me to speak at the event today. It's great to be contributing to the Carnot Battery webinar. And in particular, as I am a chemical engineering graduate of the University of Birmingham, and I have to also give credit to Yulong Ding for introducing me to the field of thermal energy storage. My name's Maxwell Cameron Jones. I'm a process project engineer within the systems integration team at Siemens Gamesa, where we are developing ETIS, an electric thermal energy storage technology. Just checking, can you also see my camera as well? Yep.
Yep.
Good. So today I will introduce you, talk to you about the trends that we are seeing for more storage, the working principles of ETIS. So how does our energy thermal technology store electrical and thermal heat? How Siemens Gamesa has developed the technology over the last 10 years and where we are at now. And also now looking into the future where we see ETIS and the different applications to commercially deploy our technology in the market. And also some market incentives that we see that the market is currently lacking, but also where we see that there maybe needs to be regulatory changes, but also some really good prospects and opportunities, including in the UK, that we see as opportunities to support business models for the deployment of long duration energy storage. So the energy transition. So we've talked today about the target of net zero by 2050. And so I'd like to take you through some of the trends that we see and expect to happen in the next 10 years that will drive energy storage at a large scale. So increased renewable penetration. We're seeing a lot across the globe, markets seeing large amounts of more installed renewable electricity onto the grid. This is causing increased levels of market volatility in terms of the system price for wholesale electricity, where we're seeing negative pricing typically in the summer for oversupply of renewable energy, and that's actually causing the price to go negative. So that's where you would get paid to take power off the grid. And also in the last recent weeks, we're seeing very high prices into the thousands of pounds per megawatt, where the system is struggling to meet the minimum demand that's needed, and we're running out of reserve power. There's also obviously a huge pressure to meet that net carbon zero, and so to decrease CO2, and some of that's being achieved through CO2 pricing. And obviously, when you're looking at a carbon decarbonization technology, the CO2 pricing helps support business cases. There's also in many countries a commitment to coal phase out. either coming from the government through regulatory requirements, such as in Germany, there's a forced requirement to phase out coal, or in other countries where as well as the UK, where there's been a requirement to phase out coal, but also a lot of coal power stations are coming offline in advance of those deadlines because they're becoming uneconomical to operate. There is also, for manufacturers and industry, such as manufacturing of steels, a pressure to become more sustainable in their supply chain, and also more carbon neutral, and offering products and materials that have a less carbon embedded within them. And also heat, and we've touched on this, today, about there being an increased amount of heat needing to become from renewable energy generation, as opposed to fossil fuel. So what are the system challenges from these demands and trends? Well, we're seeing an increased instability in the grid, and these are challenges that energy storage needs to solve. So the energy storage solution needs to provide increased stability through things like frequency response, voltage control, inertia, and grid constraint management. And that's where renewable utilization in particular needs to be enabled. So we're seeing even already today that we're curtailing large amounts of wind in Scotland. And so the energy storage solution needs to be able to alleviate the grid and allow us to utilize more renewable energy and not impede us on installing more to meet those net zero carbon targets. There's also a demand for the requirement to increase the flexibility of traditional generation, whether that's nuclear power stations or even, say, high efficiency coal or even gas, some applications, where then there needs to be more flexibility to allow them to be participating in this renewable energy system, where you're needing to turn down your generation, and that can actually come from a transmission requirement. To be connected to the grid, you need a certain level of turn down and rate of turn down. And also security of supply. And as I said, the last few weeks, we're seeing high electricity prices, and part of that's coming from the lack of security, and that we're coming close to our maximum capacity with a number of events in the grid occurring at the same time. So the energy storage solution needs to be versatile. It needs to be able to apply to a number of different applications. It needs to be scalable, because we're seeing this huge opportunity for energy storage, and so the technology needs to be scalable, but at the same time being clean and safe for the environment, but also geographically unrestricted, and this has been touched upon. The largest energy storage technology out there at the moment is pumped hydro, but obviously they are well developed, and also there is limited opportunities for new sites, and they're also very environmentally damaging for new developments because of the large amount of land that they need to achieve the capacity, but also low cost. So the solutions need to be financially feasible, and to be able to compete in the short term potentially with things like gas peakers, but also in the long term to be make sure that our electricity prices don't continue to increase through managing the electricity network as opposed to actually the source of the energy. So we're seeing a decrease in the price of electricity from renewables because it's free, right? The renewable energy doesn't cost to operate. However, seeing an increase in the cost of grid stability, and energy storage should offer a reduction in that cost with its solutions. So how does ETIS contribute to solving these challenges? We are seeing that there's an opportunity for ETIS that sits within the middle of a number of different applications and services that we can provide. ETIS sits at the larger scale in the gigawatts and hundreds of megawatts of capacity, and thus duration to supply or charge from the network. And also, based on the components that we use, we're able to scale into the tens of megawatts or even hundreds of megawatts where the application requires. So that allows us to sit above grid stability. So that lower end in the capacities and power is being met by batteries in the frequency market, for example, but ETIS isn't really looking to compete with that. We are looking at increasing that utilization of renewable energy by alleviating things like grid constraints, We're able to supply security of supply, which is needed for long duration and high power, by putting electricity back on the grid. But also we meet the industrial demand for increased flexibility and decarbonisation of industrial industries. So what are the benefits of ETIS, and why would you choose ETIS in these applications? So we're able to go up to high temperatures, which offers efficiency and industrial applications that maybe other more efficient but thermal energy storage technology is able to offer, but ETIS is able to meet those high temperature applications. We're emission free, we don't emit any emissions, and this also helps in permitting and deploying the technology. And we're large scale, so flexible to meet those large demands for both power and capacity, as mentioned. But we can also provide heat and power, and I think that's an advantage of a thermal, that is the advantage of a thermal energy storage technology, as opposed to, say, a chemical electro battery system. We can also supply the heat, and I think quite often that the heat requirement for energy storage maybe isn't always looked at by the market or some of the financial models for energy storage. It needs to be customizable, and as I said, it needs to fit the client's or project requirements to be financially and technically feasible. We are using non-hazardous and materials. We don't cause harm over the lifetime of the deployment of the technology, and we have a long design life, so we're not needing to be replaced after many cycles. We can do many cycles, and this is obviously often a metric looked at for batteries, and thermal energy doesn't tend to have that same problem that we've seen in our technology. And as I said, ungeographically constrained, and also provide localized benefits for where the technology is deployed. So I'd now like to take you through the working principles of ETIS, and I've got today a model, an animation of our demonstration plant in Hamburg that shows you the full cycle of the system. So here we've got both the ETIS technology and also a water steam cycle. So the water steam cycle allows us to discharge electricity onto the network, and the ETIS system allows us to charge from the network. So the main components are the storage unit, the blower and the heater, and also the steam generator. So they're the core elements of the ETIS technology, and as I said, they're attached to a traditional steam water cycle. So starting from in the charge mode, we look at the blower, where you can see the blue is representing the cold air transferring into the heater, whereas it heated up to the high temperatures of up to 800 degrees. And here you can see the hot air entering the storage unit and filling and heating that material, which I'll explain in a minute, to those high temperatures. The energy is then stored within this concrete bunker, insulated concrete bunker in the rock material. And then when we want the electricity back, we use the blower to blow cold air, as you can see in blue, to force the transfer the heat from the storage, from the rock material back into the air. This high temperature air is then transported to the steam generator, where you can see the temperature change from high temperature to low temperature, where it is then sent back to the blower and recirculated through the system. So here we now have a traditional water steam cycle. So the water is boiled using the hot air from the ETIS system. It is then sent to a steam turbine in a traditional manner of a traditional coal or gas power station. And this is particularly similar to a gas power station, where instead of having the exhausts of a gas engine, you're using ETIS. And I'll explain how this is an application later. And as in a traditional water steam cycle, the water steam is condensed and returned back to being reheated. So here we've got the whole system, and I'll show how we've developed the technology and the fact that we've got the full cycle in Hamburg, the demonstrator site, showing how the technology is working in principle and is not just a concept, but also practically feasible and being built. So going into a bit more detail now. We look at the elements of the storage system and their advantages. Oh, sorry. Oh, okay. I hit the wrong button. Go back. There we go. So looking at the elements of ETIS and the particular advantages for each of our components that we have selected to use to store the thermal energy and store the electrical energy. So we charge using an electric resistive heater. The advantage of this is that we're able to achieve high temperatures. The electric heater converts that low price electricity into heat, and by the fact that we're using this heater, we're able to respond fast and quickly to the load that is demanded to be taken off the grid. We're using air, just ambient air as our process fluid, and so we are not limited by the process air in terms of the temperatures that we are able to reach. And it's all within a gaseous, the air remains as a gas, so we're not looking at a phase change in the process fluid. And then when you look at the storage material, we're using volcanic rock, and we chose this because it's a low-cost, abundant material that can be sourced from globally. So whether we've got a project in South America or in the USA or in Europe, we're able to source that material that we need a larger amount of locally. There is no phase change of that material, so we are just looking at the specific heat properties of the material by increasing its temperature to those high temperatures. The heat is then stored within the rock material by having an insulated concrete container that is able to store the energy for many weeks with only minimal temperature degradation of the thermal store. And the advantage also of using this low-cost material, both in the storage material itself, but also in the container being a standard construction material, is able to then build multiple modules and scale to those large energy storage requirements of capacity. So as I said, into the hundreds of megawatts of thermal and energy storage. So when we want the electricity back, or we want to discharge the system, we then look at the discharge process. So here we are using the blower to blow that cold air over the storage where it's being transferred, and here the air is being heated up to those high temperatures and able to then transfer to the steam generator, as we saw in the animation. But that hot air can also be used to generate steam for other applications, so for industrial steam networks, or even for industrial applications that need high temperature air, such as in the steel industry and manufacturing process. So we're actually quite versatile on the discharge part of the technology to meet those different applications. It's also, if we look at the efficiency of the system, the heat-to-heat efficiency is very high because we're not changing the fluid, we're not doing a phase change, we are just heating something up. We're mainly looking at heat transfer mechanisms. Which means that the heat-to-heat efficiency is in the high 90s in terms of percent. So we're only looking at those thermal losses that can be reduced through insulation. When we look at how we get the electricity back, and the technology we then used to recover that electricity from the heat, then that is where our efficiency is affected. So if we're looking at the traditional water steam cycle, we're obviously limited to the technology there with between 30 and 40% efficiency, but there are obviously other things like low Rankine, organic Rankine cycles that could be used with ETIS to increase the efficiency of discharge. But for our commercial deployment, we're very much looking at traditional steam water cycles because they are so extensively used and mature technology with their supply chain and obviously fully understanding by the industry and to the scales that we desire to be needed. So taking you now on the journey for ETIS from concept and research within project within Siemens Gamesa through to how we're now commercially ready to be deployed. So in 2014, we constructed and began testing at our test site in Hamburg. This was a 5 megawatt thermal storage capacity unit. And here we had just the storage modules, and we actually had 2 of them to allow us to test for different storage materials. And here we used a gas burner to heat up the storage material, thus to simulate the charging process. But that was important because we needed to look at how the material behaves over its life cycle. So through cycling, was the material that we were choosing the best? So in terms of its thermal properties and also its mechanical properties. And from doing extensive hours of testing in those two modules, we were able to select the material that we see as being most suitable. And when you look at that material also in its supply chain, so where can we source it, that was also included in that study. So there was no point choosing a great thermal properties material, but if it was very limited or very limited in its use, then we wouldn't want, so very limited in its supply, then that wouldn't meet our requirements for deploying the technology on a large scale globally. So then we moved into building, constructing, and now operating our demonstrator facility. And this was money funded from the German public funded body. And here we have built a 130 megawatt hour thermal storage unit. So the 130 megawatt hours is of useful thermal energy. So you're looking at what is recoverable from that thermal energy. So by looking at the temperature profile that you need for the application, and here we were looking at a water steam cycle, that is the amount of energy we can recover from the ETIS storage unit. We are using a resistive heater of over 5 megawatts. And that was important to also demonstrate that the commercial and scale that we need on the component was also available in the supply chain and technically and feasible to be deployed at this scale. And so we connected to the grid and began providing actual commercial grid services as part of the project from 2019. And those commercial products that we are providing is with our partners Hamburg Energy, and they are looking, they use ETIS in a demand response, both on discharge and charging, to support the network activities as an operator of the Hamburg local network. So overall, the demonstrators very successfully demonstrated our technology, and we have obviously gained a lot of understanding at this scale, and that gives us the confidence to take the technology and being ready to commercially deploy it, and working with engineering partners to deploy those. So we're working with engineering partners and also customers as well, to look at projects and develop projects around the world. Obviously, there's different business models depending on which region or market you're entering, or even what is the application that we're being used for. And I'll go through that in a moment, how ETIS can be used for different applications. And we're looking also at projects of much larger scale than the demonstrator. So we're taking that step up into the next grid scale, large, long duration energy storage projects now. So I've explained the market trends and the technology, and now I want to look at there's three particular applications that we see ETIS offering benefits and revenue streams for. So there's ETIS switch. So as I mentioned, there's a requirement to phase out coal. And so, and that leaves a very valuable and large generating capacity on the network from coal power stations that have been turned off, that is being decommissioned or turned off because of regulation or not financially feasible. And so ETIS can come in there and be integrated with that power station to utilize that steam water cycle. So you replace the fossil fuel boiler with an ETIS system, and that gives a second life to that equipment. And quite often these power stations are recently built. They're not necessarily very old technology or old equipment. They still have a long life span in them, and we can meet those high temperature requirements for these recently constructed power stations. So we're really utilizing the latest in the steam water cycle of technology, and then offering a carbon-free energy storage system to utilize that. So we're minimizing the capex needed to deploy large amounts of energy storage to the network, and thus all the benefits that come with it, but also providing a positive local impact by maintaining that facility's economic viability. And then there's ETIS add, and this is where we've touched on a little bit with Yulon asking about industrial heat application, and here ETIS is able to provide an add application where we're looking at decarbonizing industries by supplying a heat to those industrial applications. So electrification of the heat from maybe where they used fossil fuels technology or fossil fuel boilers or burners or generating units to generate heat. We're able to replace those or add flexibility to the site, and then thus reduce the carbon emissions of that industry and thus the products that they make, as well as providing grid services by being a flexible asset that can be utilized. So now looking at ETIS base, and here is the standalone unit, and this is what we have in Hamburg as a demonstrator. So the demonstrator is that full system, and this is what we see at ETIS, with an ETIS base. But not only can it be installed anywhere, which, as we say, is critical, but in terms of being installed anywhere where the grid needs those benefits for energy storage. And so also it can provide different output possibilities. So we can provide electricity and steam, and also supply a district heating system. So we're very flexible to meet what the local requirements are for not just the electrical network, but possibly even a heat network. And when you look at the revenue streams along the electricity value chain and start with generation, as I say, we can provide flexibility to power plants, allowing them to be economically viable to operate. We can trade with renewable electricity by offering the ability to maybe utilize those negative pricing opportunities that are happening. In the transmission and distribution, we're providing a level of security of supply and also grid stability that the transmission network is needing. And then trading and arbitrage, so you can utilize the differences in prices of highs and lows to supply not only electricity, but also heat. But also behind the meter, here we see the power to heat, where there may be an industrial user where their whole activity is behind the meter, their generation, and also their heat supply, and ETIS can be used in that application. So incentivizing commercial solutions, and that's where we've looked at the market, and we are seeing projects that are we're developing those projects and looking at those business cases. But there's always opportunity to help incentivize more storage in the commercial deployment. So we're seeing this price volatility, and that's creating this opportunity between high and low pricing. There's curtailment occurring at great cost to the transmission network. So there is an opportunity there to help reduce some of that cost for the transmission network by offering an energy storage solution. And there are also revenue streams, and those KPIs in particular, how we measure the financial viability of an energy storage project maybe on it needs to be considered, because if you look at certain metrics such as levelized cost, that may not price in, say, the flexibility benefits of an asset being installed and deployed. But then looking at the regulatory framework, so there's definitely progress, and we're seeing that in the UK and in Europe, but also there are sort of also barriers. So when we're looking to deploy more wind, the assets that are currently there are obviously incentivized through subsidies, and so they get priority dispatch onto the networks, and so there isn't necessarily the incentive for wind developers to be installing and investing in infrastructure such as energy storage to allow them to increase their deployment of wind. And so instead, the challenges and issues that increased wind deployment cause to a grid is being pushed on to the burden of the transmission operator, and ultimately the burden is pushed onto the consumer, and that's where it comes to that increased cost for the consumer, as they are paying then for the grid stability element rather than necessarily the energy that they are purchasing. And also there could be more incentives to increase flexibility. So how do you incentivize the ability to turn up power on or take power off the network? And as I said, we are seeing that coming through, and we need those to build and strengthen the business models to really incentivize the big sort of financial institutions to invest in energy storage, like we have seen in, say, offshore or onshore wind or even solar as well, where now the investment's really driven from the commercial side as well. But we are seeing, as I say, progress and some great opportunities in Europe in terms of CO2 reduction and incentivizing financially CO2 reducing technologies and projects. And also in the UK, that flexibility and grid stability service is being valued by the national grid through their pathfinders. And there are commercial opportunities there that energy storage can participate in to build those revenue stacks and the financial feasibility of a project. So with 1 minute to go, I will quickly summarize where ETIS is and how we see the technology. So we're a mature technology. So we, in the terms of the components that we are using, have an extensive supply chain. And so we're able to deliver those projects and the scale that's required and demanded by the market. We're flexible and can be adapted to those applications that are needed. We're also scalable to those large scales because of the materials and design that we use and the construction methodology. But also, I think is important is that we're economically and sustainably over the lifetime and life cycle of the technology in the plant. And we don't have a long-term environmental damage to the environment in when we're being operated or during disposal at end of life as well. So thank you very much for listening, and looking forward to taking questions in the Q&A session. I will also put the email address here in the chat to allow people to contact us with any opportunities or questions they may have.
Thank you very much, Max. Very fascinating presentation. There are certainly a few questions in the chat box. We will pick them up after the second presentation. Perhaps you might want to have a look at there. So yeah, thank you again. And I think we can move to the first presentation from academic experts. So we have Guido Francesco Frate from the University of Pisa, and he will give us a presentation about the advancements there, particularly around turbo machinery for Carnot batteries. Guido, the floor is yours.
Thank you. I will share my screen. Okay. Sorry. Okay. Sorry, just
No worries.
Okay. Oh, okay. Thank you. I'm Guido Francesco Frate from University of Pisa, and today we wanted to present some reflections and some overview on the use of two-phase machines in Carnot batteries. This is more or less the content of my presentation. After a brief presentation of my research group, we will talk about the use of two-phase machines in Carnot batteries, what technologies could we use. Then we will focus on expansion and compression, highlighting some thermodynamic and technical limitation of both, and then we will draw our conclusion. University of Pisa in central Italy, our research group, the energy engineering research group, is made up of 5 professors and 6 between PhD and postdoc researchers, but most of our activities is carried out thanks to the large number of master degree students that we supervise for their final project every year. Our research topics are more or less green topics in energy engineering, so renewable energy sources, the machines, specifically volumetric small size machine, and energy multi-energy systems. And the background for this presentation can be related to two European projects. The first one, which it's now finished, and in which one of the author, Professor Lorenzo Ferrari, one of the author of this presentation, participated in. It was about the development of two-phase expander, so right on track. And the second one, which just began in September, is about the developing of a power production cycle which operates entirely in two-phase region. So another time very suited for this presentation. About the two-phase machines, I would say that it is a limited research area, especially if we try to find experimental studies, and most of the research is focused on the expanders, two-phase expanders, and later in the presentation we also understand why. Our presentation is mainly focused on the two-phase, on machines that operate extensively in two-phase region. So we focus on machines that operates with saturated liquid and ends their transformation in two-phase region, or starts with two-phase fluid and ends in two-phase region. So we don't focus on machines that are basically single-phase machines that can handle or must handle a limited amount of two-phase flow, which is very, sorry, I don't know what is this. Okay, but these are, however, important. For example, they have extensive use in steam power cycles, or in refrigeration application and in cryogenic application. There are extensive use of hydraulic turbines. In Carnot batteries, there are a few spots, very interesting spots, in which we can use two-phase machines. The first application is to recover the pressure work from the heat pump cycle, so the charge cycle of Rankine Carnot batteries, Rankine PTS. This is particularly interesting in CO2 transcritical cycles, which are one of the technologies proposed for Rankine PTS, because the pressure work is very high here. And so we could replace the throttling valve with a two-phase expander to recover part of this work. This would increase the COP and so the charge efficiency of the Carnot battery. Another use, more specific, would be that two-phase expanders would unlock two alternative cycle configuration for the Carnot battery discharge cycle. In particular, we could use for the discharge triangular cycles, in which we have a two-phase expander that expands saturated liquid here, or flash cycles. In this case, we would use the two-phase expanders to replace the throttling valves here and here. This would be the discharge phase and would allow to achieve very good matching between the temperature profiles of the discharging single-phase thermal storage, reducing in this way the exergy losses, which are one of the main losses in Carnot batteries. This would be very interesting also because if you want to use a single-phase thermal storage and you want to do that because of the cost, which is very low compared to PCM, for example, or hybrid solution with PCM and sensible heat storage. But then you face not only the exergy losses because of the mismatch between the evaporation and the temperature profile, but also the fact that there is a strict trade-off between the energy density, which is controlled by this temperature glide, and the efficiency of the discharge cycle. With the use of these alternative architectures, you could bypass, let's say, this trade-off and achieving potentially higher efficiencies in the discharge. So two-phase expanders would be quite interesting in Carnot batteries, in ranking Carnot batteries, while for compressor it's less obvious to find an application. Let's say that two-phase compression is even more challenging. We will talk about that in the presentation. There is one, and it's even less useful, but there is one very important exception to this, one which is to approximate in reality Carnot cycles. One of the ways in which we can approximate Carnot cycle, realize Carnot cycles in practice, is to operate a completely operate a power cycle entirely in the two-phase region. And in this case, in the charge, you would have a two-phase compression here, and the discharge, you would have a two-phase compression here, this transformation. Of course, with their inefficiencies in respect to the isentropic transformation. So this would be the main application that we can think about. What is the best technology to perform two-phase transformation? Well, there is a general consensus that volumetric expanders are the best suited for this task for mainly two reasons. One of which we can see here. During the expansion, the liquid tend to move very much slower than the gas phase, and this brings to the very distorted velocity triangle. Compared to the blade that moves in this direction, the droplets end up moving in this direction, so they will hit the blade and cause not only losses due to the fact that you have to stop the liquid and to invert its motion to let it go outside the rotor, but also because you can also have some mechanical problems of erosion of the blade. Besides that, there is a rule of thumb that suggests that for each 1% more liquid fraction at the end of the expansion, you lose, compared to the dry expansion, 1% efficiency. Actually, this is the Bauman rule. This Bauman rule was revised recently for cryogenic application, in which a two-phase expander, turbo expander turbine, it is a turbine for cryogenic application, was studied from numerical and experimental point of view. And here we can see that the losses compared to the dry expansion are always higher than the suggested 1% by the Bauman rule. So quite fast, even for very little liquid mass fraction, you can lose a significant portion of the efficiency. And that's why let's say we think that volumetric machines are the best suited for this task. Volumetric expanders are very similar to volumetric compressor. Basically, they are the same machine operated backwards. Actually, it's not that simple, depending on the technology. Maybe some small modifications are needed, like the introduction of valves, controlled valves, not automatic valves, like in compressors. But anyway, volumetric compressors are a very mature technology, and we can produce volumetric expanders by retrofitting compressors, more or less, or exploiting the knowledge that we have on compressors. So we think that it is a cheaper technology than dynamic expanders. Furthermore, they tend to rotate slower, so we would not need a gearbox, for example, for coupling the electrical generator and the expander in case of volumetric machines. Of course, there are some limitations. The first one is that volumetric machines tend to have lower efficiency compared to dynamic one. Here you can see results from experimental analysis of 4 technologies. There are root, screw, piston, and scroll expanders. And besides scroll expanders, which is the most promising technology, let's say, that can achieve decent isentropic efficiencies that are somehow comparable with those achieved by dynamic expanders. The other technologies have pretty low isentropic efficiency, and so we have losses. We are less efficient than when we are using dynamic expanders. But the biggest limitation is that the fact that volumetric machines have a fixed volume ratio, which is around 5 to 6, which is the ratio between the maximum and the minimum volume inside the machine during the transformation. And if the system, this is dictated by the geometry of the expander. So if the volume ratio imposed by the transformation that you want to achieve is different from that of the machine, you end up having overexpansion and underexpansion loss, or overexpansion and underexpansion losses, because you are forced to expand less or more compared to the pressure that you want, because of the fixed volume ratio. So for large volume ratio, like those involved, as we will see later, in, for example, expansion of saturated liquid, we would need multi-stage machine to achieve the right volume ratio. If we focus on the expansion, we can say we selected a case study. We think that it is representative of triangular cycles or flash cycles, and even the recovering of pressure work from heat pumps, high temperature heat pumps in this case would be. We assumed an isentropic efficiency for the expansion, and we varied the inlet quality just to perform some simple calculation and to have an idea of what the fluid looks like at the inlet, given the different steam quality at the inlet of the machine and at the outlet. Is it liquid with mostly liquid with bubbles inside? Is it mostly vapor with droplets inside? This is different, and you cannot see from the vapor quality, which is the mass ratio. But you can see, if you look, you can see this effect. You can at least have an idea of what kind of flow you have if you look at the volumetric ratio at the inlet and at the outlet of the machine. And our results, our simple calculation results are, for example, this one. Here we have the inlet steam quality, vapor quality for different fluids, some organic fluids which are suited for this temperature level, and water. And the first results that we can see from this picture is that water is very different from organic fluids, which could be a problem because most of our understanding of two-phase transformation is from application with water, but actually water behaves completely different from organic fluids. In particular, for water, just a very low inlet quality let the fluid be in terms of volume mostly gas, with very few volumetric, very little part of the volumetric flow rate is composed by liquid. And while for organic fluids, these happen at quite higher inlet qualities. Let's say we have the 90% of the volumetric flow rate is vapor only if the inlet steam quality is higher than 0.4. So we basically have an almost single phase expander for values higher than 0.6 for the inlet quality. While at the outlet of the expander, we always have that the vast majority of the volumetric flow rate is gas phase. This is interesting, but the even more interesting is that if we look at the volume ratio in function of the inlet quality, we start from saturated liquid and we finish up in a normal single phase expansion. We can see that the volume ratio required by the transformation is much higher than that can be achieved in a single stage volumetric expander. And this tells us that, for example, the direct expansion of saturated liquid would have high losses for under expansion losses. And if we want to, since it's very interesting, even for triangular and flash cycles, but also for the recovery of pressure work in heat pumps, maybe it's better to think about slightly modified layouts for these cycles and transformation. For example, we could have a little throttling before the expanders to reduce very much the volume ratio that is required for the transformation, and then perform a transformation without any losses, maybe using two-stage expanders. Or maybe we can have a partial evaporation in the heat exchanger before entering the expander, and this will have the same effect. And in this way, we could reduce a lot, for example, under expansion losses. I think that is interesting to focus on some phenomena that really differentiate two-phase expanders from single-phase expanders. The first one is this one that we can see here, is from an experimental analysis of a screw expander, and we can see that compared to the expected pressure trend in function of the volume of the swept volume during the suction and the expansion in the machine, we can see that the suction that for single phase is operated more or less constant temperature, and then from this point, let's say, starts the expansion. In two-phase expansion, the suction is with a significant pressure drop. And this is due to the fact that you have to accelerate the liquid, the fluid, the two-phase fluid, before for letting it enter the machine. It's the same that happens in the nozzle of a turbine. And only after that you can start the actual expansion. And what happens is that you have quite larger pressure ratio for the same volume ratio than expected. Is easier to fall in overexpansion, to have overexpansion losses, because you don't expect this pressure ratio here. And then this, what you have is that you can suck in less mass flow rate, and so you have a lower filling factor or volumetric efficiency for the same machine. And this problem gets worse, of course, when the rotation velocity of the machine increases, because you have to accelerate the fluid even more. The other problem that the other technical issue that is interesting to outline is that actually in two-phase expansions, you don't have the thermal equilibrium between liquid and gas phase. And you can see very well here in which in this paper, this is an experimental analysis about a piston expander. The authors compare the measured cycle with the expected one, which was calculated assuming the thermal equilibrium between single phase and vapor phase. And you can see that it fits very well, except for the expansion, in which you have a significant difference. And to account for this difference, what you have to do is to account for the non-thermal equilibrium between gas phase and liquid phase. Actually, the characteristic time of the phase change is higher than the characteristic time of the change in volume, which is imposed by the piston movement. And when the piston goes up, a part of the liquid suddenly evaporates because of the reduced pressure, but this lowers the temperature of the gas phase, and then the liquid must, there is a heat transfer within the liquid and between the vapor phase and liquid phase that balance back this, latent heat that is required for vaporizing the liquid. And if you take that into account, you can find very good agreement with experimental data. And since it is related to the rate of change in volume in the machine, and with time, you have that the difference is quite high at the beginning of the expansion, while it reduces a lot towards the end of the expansion, where when the heat transfer and the volume change rate can keep up with the expansion of the gas phase. Moving to the compressor, we selected the reverse case study with the same assumed isentropic efficiency, and we performed the same calculation for understanding what is the nature of the fluid we are dealing with. In this case, it's very interesting to notice that water is behaving another time different from organic fluids. But what is really interesting to notice is that while at the inlet of the machine, even for quite low inlet qualities, we have mostly vapor. At the end of the compression, if the inlet quality at the start of the machine, it is not higher than 0.45, 0.6, let's say, you may end up with only liquid at the end of the compression, which is very dangerous for the equipment. If you end up without if you end up with too much liquid, let's say, there is a very high risk of compressor failure because of a phenomenon called liquid slugging, which is covered in a few slides later. It is the same. The volume ratio trend is similar to what we observed for the expansion. This peak here is when you reach liquid at the end of the compression for lower inlet steam qualities. You are performing a almost liquid to liquid compression, so the volume ratio is decreasing up to even a number just slightly over 1 when you have just liquid in your machine and it's incompressible, let's say. It is not that most of the research about two-phase compressors is focused on avoid liquid at the suction of the compressor because of the risk of ending up with just liquid and destroy the compressor. Actually, a limited amount of liquid at in the compressor is beneficial up to a steam quality equal to 0.9, because this is one of the main techniques to reduce the discharge temperature in the compressor. There are some ways to do that. You could start with the two-phase liquid at the suction. You could inject liquid and two-phase fluid directly inside the compressor. But every time what we are trying to do is to avoid entering the two-phase region or just having a limited amount of liquid at the suction. This could be very beneficial. It may expand the operating range of the compressor. But if the inlet quality is too low, what happens is basically liquid slugging, which is a phenomenon due to the fact that inside the compressor, the gas phase tends to move faster than the liquid phase. So it tends to exit the compressor before the liquid. So at the end of the compression, here we have the actual compression, then the discharge. When you arrive at the end, you only have liquid, and you may experience this sudden pressure spike that could destroy the compressor, basically, if it's too much. And this is a very important problem. There are cases in which you are forced in which you want to avoid this regime, but you are forced by of design or cold startup of the refrigeration system, for example, you may end up having this problem. But this, for our perspective, tells us that with standard equipment, two-phase compression is very, very challenging, because it actually is dangerous for the equipment itself. And of course, liquid slugging gets worse and worse if you reduce the inlet quality, if you increase the portion of liquid inside the machine. And if you, since it's related to the different velocities inside the compressor, it gets worse if you increase the rotational velocity of the machine. And so two-phase compression with standard equipment would be unfeasible for, could be unfeasible for inlet qualities lower than 0.9. So our conclusion is that while two-phase expansion can be successfully achieved with volumetric expanders, the compression is more challenging, and we might have to think about different non-standard equipment to do that. For example, to perform, if you want to perform a two-phase compression, maybe you have to use different pump and a compressor and then mix it again, something like that, but not just a compressor. A regular compressor cannot work in basically in two-phase conditions. It's very risky. However, the two-phase expansion can be performed with volumetric machines, so you have the problems related to fixed volume ratio and a reduced isentropic efficiency, let's say, in most of cases. And very interesting phenomena, to me at least, is that you actually have to take account that the expansion is quite fast, and there is no equilibrium between liquid and gas phase during the expansion, and you have to take into account because introduce some losses. These are all the bibliographic details, interesting papers and papers from which I took some of the pictures that I showed to you. And thank you for the attention. And I will be glad to ask to answer to some questions.
Fantastic. Thank you very much, Guido, for this very comprehensive presentation. So, yeah, please drop your questions in the chat box. There are a few that came in already for both Max and for Guido. So we have about 15 minutes for questions. So I will perhaps read aloud some of the questions that came in, and looking forward to hear from the presenter. So perhaps I start with Max, while attendees might drop more questions for Guido. So Max, I have perhaps grouped and gathered a few questions that to my eyes seems, let's say, similar. So perhaps I'll start with one about if you can give more information about the discharge rate of the system, and similarly, which time scale can this system deliver commercial grid services?
So that's where ETIS has its benefits, in that you can design and configure the not just the storage unit, but also the air system. So the air system being the blower, the heater, and the pipe work to whichever scale in terms of power rating that you need for the project and its application. Obviously, you then have a fixed design rating for the storage equipment, but obviously then there is also the turn down opportunity and possibility by using the blower to provide the power that you'd need. And I think that was also one of the other questions possibly, was the ability to turn down to meet those grid surfaces. And that, in terms of the duration, again, it's configurable. So you can either make a larger storage single unit, or also look at building multiple modules out. So if for those larger capacities of storage, so you build, say, 2 or 3 multiple modules in parallel.
Thank you very much. Perhaps I'll ask a question from my side. So is the system therefore suitable for primary reserve as well? So things like frequency response or similar services that are, let's say, available in the UK, potentially?
So yes, in terms of the charging side, the heater can respond very quickly. So you would be fulfilling the frequency, was it the over frequency events with your heater by taking power off the grid. Obviously the discharge is limited by the discharge technology. So depending on how you generate that electricity and how you can, say, configure the system, but it's then a limitation of, say, this if you're using a water steam cycle. So partly yes on the charge, but partly yes on the charge, but more challenging on the discharge. But again, depends how it's configured.
Okay. Fantastic. Perhaps I'll take one question for Guido and then come back to you. One question came early during your presentation, Guido. So you mentioned in the supercritical CO2 cycles. So in what temperature range would such a cycle operate, and why could be useful?
I'm very sorry, because actually I was, it is my mistake. I was referring to transcritical CO2 cycles. Now, because there are some examples of supercritical cycles used in Carnot batteries, but they would not benefit from two-phase machine because they're basically just gas cycles with CO2. So now it's my mistake, actually.
Thank you. Thank you, Guido. I lost briefly my connection. So I guess you also addressed the second question, perhaps. It was about the transcritical and supercritical cycle. Perhaps I have a, let's say, a follow-up question from my side. So during your investigations at the University of Pisa, have you seen, let's say, what sort of benefit you would have by implementing these machines on Carnot batteries? What sort of, let's say, increase in round trip efficiency or key performance indicator you would expect at, let's say, Carnot battery level?
Not yet, unfortunately. It's something that we are thinking at the start of the presentation. In the very first slides, there are some ideas that we have. We didn't still investigate that. I would say it is quite promising, however, because the discharge efficiency in running tests with low temperature application like heat pumps and ORC cycles, the ORC is it has a very low efficiency because of the temperature level. So basically it is not you could, the triangular cycle is in principle less efficient than the ORC, the standard ORC, but you could gain very much on the thermal exergy saving side. And so it could be interesting, but we did not perform yet some calculations. Sorry.
Okay, fantastic. I think we'll come up soon. I will certainly be interested to hear more in the future. Okay, perhaps I'll take one other question for Max. Actually, a couple of questions in my eye, very similar. One, is there any more data available from the demonstrator, like completed cycles or measured efficiency? And similarly, if you can comment on what you have seen in terms of evolution of the rock temperatures during the discharge cycles.
So in terms of data, not currently publicly available, but in terms of how we see the system and how we see that temperature profile through in our storage, the demonstrator has demonstrated that the thermocline through the storage material is maintained very well, and what that means is when you charge with those high temperatures of up to 800 degrees and you transfer the heat into the storage, on your discharge you maintain a high temperature throughout the discharge process. So you don't see a drop off or a sort of a reduction in the quality of the heat until you get right towards the end of the storage's capacity. And that's when I quoted the 130 megawatt hours, and that's how that number is calculated. So we build the capacity to meet, we design the system to a capacity and don't expect the temperature to drop off towards, say, the end of a charge. So the 100% is 100% and 0 is that point that we lose that temperature, but that doesn't happen, and it happens quite quickly.
Okay, thank you. Perhaps I'll take the opportunity for a question from my side, still on the temperature profile. So as far as I understand, the thermal store is a horizontal packet bed.
Yeah, that's correct. Yeah.
Do you see, or have you seen any issue with the bypass of the flow? Typically with horizontal packet bed, you have a, let's say, larger issue at the top of the packet bed due to gravity reasons, and on the other side, buoyancy acts against you in horizontal packet bed. It tends to disrupt a little bit the front of the sharpness of the thermocline. Anything, any thoughts around that?
So obviously that is a phenomenon that's seen, and we understood that and saw that and was able to understand that in our test facility and how that works. But part of the IP of ETAS and Siemens Gamesa is the design of the storage unit to prevent that phenomenon occurring of bypass flows and disruption to the thermocline. So that's something that's inherently designed into our knowledge and of the storage, and also thus mitigated against in the design that we've built. Okay,
fantastic. Perhaps some sort of internal structure or partitioning type of system to avoid this type of bypass. Will interesting to hear more, obviously. Okay, obviously, if anyone has more questions, please drop them in the chat. I've probably a couple of questions for Guido. So if you can, let's say a few words about where do you see the limit in terms of vapor quality at the, let's say, inlet or outlet of your two-phase flow machines? So what sort of liquefaction you might expect for an expander or for a compressor?
For the expander, there are no limitations. There are the limitation that we saw in the presentation, in the sense that you have not volume ratio that are not right for the machine or for the most common machines, volumetric machines. But apart from that, you can perform the expansion quite easily. The compressor, you have to avoid any, for sure, inlet quality lower than 0.67. 0.9 is doable. In the middle, it depends on the fluid, on the temperature, or if you go on off design, and so you end up compressing outside your desired region. And, what is very interesting, if I may add something, is if you want to perform an entirely a cycle or a transformation that starts from two-phase to two-phase, it's very challenging to understand where are you to measure and control such transformation, because actually there are no commercial solution or very few commercial solution for the quality measurement, inline quality measurement, which would be needed for the control of the cycle, for example. And so this is actually a very big concern, especially for the compressor, because if you go too much on the liquid side, you may destroy the compressor. So it's very important to measure precisely the starting point.
So it seems that there's a need of development also from sensor perspectives for exploit at the best these technology, these machines. That's interesting, fascinating. Yeah, see another question came into the chat for Max. If you can give an indication of the basically percentage of heat losses during storage up to some weeks or up to a certain duration, and can a sufficiently thick bunker cope with the temperature losses due to high temperature inside?
So we've seen at the demonstrator site, because we're now at that large scale, that the losses are very minimal over a number of weeks, and we're only, in terms of temperature loss, it's minor, and it doesn't necessarily significantly reduce the capacity of the storage, and that is due to two reasons. One, the insulation, as you mentioned, we've designed that to a high enough level to keep the heat within, but also because of the sort of shape design chosen and the bulk material, there's actually a relatively low surface area to volume ratio, and that helps again reduce the thermal losses from the storage unit. And obviously with larger systems into the hundreds of megawatts and even possibly gigawatts, you see an increased benefit in the sense that you have less thermal losses. So that again is an advantage to our design.
Thank you very much. I see Yulong raise his hand. Please, Yulong, if you want to ask your question.
Max, my question is about how the heating is done. So are you initially heat air, or you are heating the particle beds?
So we use the electric.
Clearly, there are challenges for.
Yes, so we're utilizing a developed heater, electric heater, in terms of the equipment that's used in industry for heating air up to high temperatures. So we're using the blower to blow the air over those heating elements, and getting to those high temperatures from directly converting from electricity to the heat in the heating elements. And then the actual transfer process onto the storage is then a sort of a packed bed heat transfer mechanism. So it is simply the high temperature enters at one end, and the temperature drops off as it's transferred into the storage material, and then it's discharged at a lower temperature on the outlet. And because of the sheer volume of material, it's very effective at taking that heat out. And then on the reverse, it's obviously the reverse there, you're blowing the cold air into the storage bed, and so it means that actually the cold end doesn't see those extreme high temperatures. It's just a hotter end varies, as the sort of diagram simulation showed a little bit.
Thank you very much. So we are near the end of this Q&A session. Any last burning question for the speakers? We have a couple of more minutes. Christos Markidis raised his hand. Christos, please go ahead with your question.
Good morning. Thanks, Adriano. Well, I think since you said that some time, I'll throw something out there, which is a little bit of a thought. But the way I understood this is we're talking about storage systems, which necessarily have to be small scale because you're discussing, unless I'm mistaken, so please jump in, but you're discussing volumetric machines for compression and expansion, and I suspect that this is applicable to small scale systems. Otherwise, you'd use turbo machinery, right? And so the issue that we have here is, okay, small scale systems are not, you're starting to get into competition with batteries, first of all. You could argue that, okay, but these are good for longer term storage than batteries would do. But having small scale systems that store heat for prolonged periods of time is not necessarily competitive because you have very large surface areas per unit volume. So I'm not saying there's no role for it. I just kind of have a feeling that, these are niche applications where you will necessarily have these kind of almost conflicting requirements, that it has to be small, so it has to be distributed in some way. It's not centralized, it's not grid scale. It's not hundreds of megawatts and you're using volumetric machines, right? But at the same time, the advantage is, of course, okay, you're storing heat, so you have, so you need to play to those strengths, I guess. It's really just a comment for or sort of an opening for you to discuss. Guido, if you want, go ahead.
Yes, you are right. I would say that we don't know. All the people that is working in this field, I don't know that there is someone. We all have our ideas, maybe strong ideas, but we don't know. I think that your point is right. We have to avoid the competition with batteries. Otherwise, we get crushed by batteries. I think there are applications in the scale of megawatt up to 10 megawatt that could be interesting for Rankine tests, let's say. And in that case, you can use volumetric machines. There are volumetric expanders, depending on the fluid, can be quite big in the scale of megawatt. It's not common. It's not but it was the starting point, because actually the research on screw expander began in 80s or even before for triangular or flash cycles in geothermal applications. So they have superheated water in that case. And they build some big expanders in the scale of megawatts. So you're right, we cannot go on the grid with this technology, but we are not limited to household or a neighborhood. Maybe something a little bit bigger we can achieve. But otherwise, yes, we have to pay attention to the size and to thermal losses.
Thank you, Guido.
Thank you. Thank you very much for the question, which I believe probably will emerge over and over also during this workshop tomorrow as well. So we are on time. So I would like to thank again the speaker, Max and Guido. So we have now about 15 minutes for a coffee break. So this will be the time where we gather around the coffee. If we were under normal circumstances, this is not the case this year. So please enjoy your break, your coffee break, and please come back at 11:45 UK time. So see you in a bit. Welcome back to the webinar. So I hope you had a good break, and we are ready for the second part of the agenda of the webinar for today. So we have a couple of more talks, again, one from industry, one from academia. So the first one is from MAN Energy Solutions, from Emmanuel Jacquelemont. Emmanuel, can you hear us? Are you out there?
Yeah, I can hear you.
Fantastic.
Can you hear me?
Yes, very well. Let's see if you can share the screen.
Yeah, I'm there.
Yeah.
And I can share my screen. You should be able to see.
Yes, very clear. Yes, the floor is yours.
Okay, thank you. So my name is Emmanuel Jacquelemont. I'm working at MAN Energy Solution in Zurich. Yeah, we are now quite a couple of years developing this so-called also ETS Carnot Battery, but we call our system 3-generation Carnot Battery system. So I'm going to explain that. And yeah, one of the solution to address decarbonization and on one side and sector coupling on the other side. These are concepts I'm going to explain and make a brief presentation of the system and where we stand now in the actual development. Well, motivation behind Carnot batteries or energy storage system, thermal or other, are clear. I think, yeah, they are linked to the integration of renewable and of challenge between mismatch of demand and production and intermittency of the production of renewable. That's, I think, quite a common and obvious fact. Where we come from with our system, we would like to approach the problem from a different side, and not only the pure electrical side. We do think that to address and have a significant impact in decarbonizing industries or the conception of cities, the first part to be taken at is the heating and cooling demand, which represent more than half of the whole overall CO2 emissions before transport and other sectors. And one also big share of this 51% is covered by actually moderate temperature processes, so up to 120, 150 degree for, let's say, yeah, common application, public or private application process or municipalities. And we do think that, yeah, having solutions how to address like the mismatch of electrical demand and supply, that's one part, but we also need to take a deeper look at how can we try to decarbonize the heating and cooling demand. And that's where we come with our ETS concept, so also called electrothermal energy storage system, but based on a heat pump technology. I'm gonna explain that in a minute. So just in terms of capacity, similar to other system we have seen before. So we are moving now there in the range of yes, 2 to 100 megawatt in electrical power rating, and in charging and discharge time from a couple of hours to make maybe 1.5 days, not really more. Okay, maybe 100 megawatt would be, yes, already a big system for this thermal ETS CO2 based system. The 2 megawatt one will be rather a small one, so a typical commercial application will be rather in the range 20 to 50 megawatt. But we can always downscale, and we can always multiplicate, so put together several systems in parallel. So yeah, we can reach also bigger capacities. these systems, so ETS based, stores energy in the form of cold and hot water. And that's where we come to the concept of sector coupling, having cold and hot water in a moderate temperature in our system. We could actually use this system not only as a pure electrical to electrical bulk system, but also to dispatch energy in different forms. So in form of cold, in form of hot, and retransfer or transform electricity back to the grid. And there are very plenty of applications. It's very hard to have an application which fits for all the needs at the same time. So that's where we come to the sector coupling. We need to couple sector or applications together in order to have significant impact on this cold hot decarbonization challenge. And when we speak about sector coupling, we need also to speak about collaboration between industries, maybe between different sectors, also private and public, which is obviously still not established. And we like to rise the thinking for politicians, for developers, for city planners, how to couple all the sector maybe better together in the future, so to have a positive impact on the whole energy demand, so in a broad sense. Now looking more into, let's say, some diagram and some details. In principle, this system works as a heat pump, so we have the benefit of like the demultiplication factor of the COP of a heat pump system. So with 1 unit of electrical energy, we can produce and store much more units of hot and cold storage. The hot storage is a sensible storage, that's simple, that's water. And the cold storage, that's also simple, a little more complex because it's ice, so latent storage from water forms to ice. And having this storage, then we can begin to play, and we can, depending on the application of or depending on the system, we can rather optimize the thermal, so the hot thermal export, if that's the priority, or the cold thermal export, if that's the priority, or if the priority is really to reach the best round-trip efficiency on the electrical side, then we can optimize the heat engine process, and then we get what we get on the hot and cold side. And as you see, that's very flexible system. First in the design, because many parameters are free to set, so very customizable. And on the other side, in the operation also, because having a certain storage at disposal, you can decide maybe in day one to export more heat and not having the need maybe of re-electrify your energy, and maybe in the day two, when the price, the electricity price is higher, you will rather decide to compromise the thermal storage, and for that to optimize the electricity production. And that's where we come with this concept of 3 generation system. Now, how it works in the reality, we have been presenting the system a couple of times already in the Carnot Battery symposium, or inside this annex. I don't want to come too much into the details of how it works, because we have done that before. You have also a YouTube animation. If you type ETS MAN on YouTube, you will find a nice animation where it's explained how it works. So basically, the circle here in the center, that's the CO2 heat pump cycle, with both evaporator and so-called condensator. That's not real condensator, because we are here at supercritical CO2 conditions. And so we use electricity, we drive the compressor, we compress the CO2. On the one side, we transmit the heat to our hot storage at different temperature level. On the other side, we evaporate CO2, and by this way we take energy from a certain energy source, which is water, and is transformed to ice. So that's the heat pump process, or the charging process. Now we can reverse the process in an RSC cycle by keeping the same storage components, the same heat exchanger on hot and cold side, but different unit for the turbo machinery. It's at the moment impossible to couple, let's say, the compressor and the expander in the way to make both cycles together with the same machinery. So here we deal with liquid pumps, or liquid pump which compress or rise the pressure of CO2, and we retrieve, sorry, I need to come back. We retrieve the thermal energy via the heat exchanger. Then here by high pressure, high temperature conditions of CO2, we expand through turbo expander coupled with the generator, and we produce electricity back to the grid or any kind of application. Then to close the cycle, we need to condense this flow, making use of the ice that we have charged previously. And once the storage is full of liquid, so when it's fully melt, then that's the end of the process, and we need to recharge it again. Why CO2 is the adequate fluid for such kind of moderate or one adequate fluid for this kind of process? I think it has been pointed out also by Guido Frate before in his studies, and there are plenty of studies and papers in the design of a transcritical CO2 cycle. We have actually developed this system together with ABB, which developed this system actually some years ago, and now we collaborate with them for real projects. So that's why just a comment. I was speaking about the CO2. We beneficiate of a very high transfer heat transfer properties of CO2 on both. Transfer between CO2 and water for the storage side, and on the other side for the turbo machinery, which can be really compact thanks to this very high power density. There are other advantages of CO2. It's non-flammable, non-ATEX, non-toxic. It's cheap and yes, available everywhere. And also, last but not least, it is available for very high capacity industrial heat pump or other kind of processes. When we want to upsize the system to really large number, like over 20 megawatt, 50, 100 megawatt, we begin to have an issue with fancy refrigerant in the sense that having too much mass of them, it represents a certain risk in case of failure or in case of damage, and CO2 in this sense has some advantage. Well, about the components which are used in the system, that's actually well-known technology: compressor, expander, heat exchanger, ice storage, and hot storage. The center part of the system, like the kind of technology, pearl, we can say, of the whole system is the so-called HOFIM compressor, which is a hermetically sealed compressor, so with an integrated motor and non-oil bearings. So we drive this compressor on magnetical bearings. So we have no emissions, no losses, and this is very reliable, based on a very long tradition of design technology of MAN. Now, if we look at the different configuration of the system coming from the right part, the system can be split in the pure heat pump system. By adding the storage functionality on the both hot and cold side, we call this system then system ATS Lite. And then the full Carnot Battery system is called 3TES or ETS or Carnot Battery, whatever the name, and that's the full system. And we develop and we offered kind of the three typologies. Here you have a overview of this typical pilot plant. It could be so designed on the paper. It has not been built, but that's a reference design we have done by sizing and optimizing all the components. As you see, this system has a certain impact in footprint. So if we compare here the footprint, that's a 7 megawatt electrical system and 200 megawatt hour thermal capacity storage, and it has the size of roughly half of football field. When we speak about this pure heat pump system, so taking the compact turbo machinery part and stacking together for a skid for a heat pump processor. So without the storage, it's much more compact. So we see that the major place requirement is used by the storage, the hot and cold storage. So here you get an overview of like the design limitation in terms of charging, in this charging time. I've spoken about that in my previous slides. So in the range, we can develop this system and customize this system. When we speak about application, I'll also briefly touch that. So different public or private sector, especially in the district heating or district cooling, which is growing up now, or any kind of process industry, process industry. Now that's some novelties. We tested our heat pump system in our test bed in Zurich last November. We wanted to validate our calculation and our process, also the whole turbo machinery part, and that's what we could achieve some months ago. So yeah, this is working as we planned, and we could test the system with roughly 2 megawatt electrical power consumption and 5 megawatt thermal. We were there limited by the thermal capacity of the system. So 5 megawatt thermal was the maximal duty we could achieve with this system. And that's yes, my last slide, just giving a couple of summary points. So the system working with CO2, possibility for decarbonizing different sectors, especially the heating and cooling sector, also the electricity, in a moderate temperature level, very scalable and flexible, and yeah, ready to implement. Yeah, at this point, I'm glad to answer your question in a later stage.
Thank you very much, Emmanuel, for the presentation. So yes, there are a couple of questions already in the chat, and I welcome everybody to drop the questions there so we can take them later. So we can move to the second presentation before the questions. So if Emmanuel, you can stop sharing your screen, please. Thank you very much. So the second presentation is from Professor Nazar Sayam from the City University of London. And so Nazar, if you are there, please share your screen and the floor is yours.
I hope I still have the 15 minutes.
Sure, yes, absolutely.
Thank you. Thank you for inviting me for this talk, and I'm glad that to hear all these presentations. Very interesting workshop so far. This presentation is for myself and Dr. Martin White, who is my colleague. Unfortunately, he could not make it for personal reasons. So I'll be doing the whole presentation, and it focuses on the challenges and opportunities for the development of turbo machinery for non-ideal working fluids. So we are based in the Thermofluid Research Centre at City University of London, and we have what we call a Turbomachinery and Energy Systems Research Group with about 15 people. The Thermofluid Research Centre, we've got about 50 people working between researchers, academics, and PhD students. We talk about the role here of turbomachinery in the Carnot batteries, and took this from the literature just to show where our work could fit in. Of course, we work directly on the power generation rather than the Carnot batteries, but it's directly linked. So turbomachinery could fit on either end, on the compression of liquid or vapor, and on the primarily on the thermodynamic cycle where you release the power, where you have the expansion of vapor or the working fluid for that matter. And our work could fit on the objectives of having a high round trip efficiency, which requires efficient expansion and compression. But also turbomachinery is likely to make the key components, although we've seen earlier that you may have two-phase expansion, volumetric expanders, for example, but for large machines, it's almost universally known that turbomachinery are the right solution. So our work really is to improve the current understanding of power cycles with the aid of component, which will aid the component development. So among other things that we're working on, we have a lot of work on gas turbines, micro gas turbines, but with respect to this particular work, we work in two cycles. The Rankine cycle, where you've seen some of it using the refrigeration or organic fluids. And I will show in a minute what work we do on that. But also we have now substantial amount of work on supercritical carbon dioxide cycles. So these come in different, if you like, temperature ranges. So for the organic Rankine cycles, we look at power generation from, relatively speaking, low-grade heat between 80 and 400 degrees C. And for the supercritical carbon dioxide cycle, we're looking at a higher temperature range, though some overlap between 350 to 800 degrees C. And of course, the ultimate goal is to produce power. The work really, we work in non-ideal turbomachinery basically, and the research at City is focused at the moment in three funded projects. The first project is we call it the Next ORC. This is an organic Rankine cycle. It has been running since 2017, now extended to 2021 due to the pandemic. And this particular project aims at conducting fundamental studies. Here we're not looking at high TRL level, so this is up to TRL level 3 on organic Rankine cycles. Three primary objectives for this project is to conduct simultaneous fluid and cycle component optimization, but also look at mean-line turbine design and performance models, and as well as characterization of non-ideal compressible flow dynamics. And with that, we do, of course, a lot of theoretical work, but we have constructed, as you'll see later, a unique test rig to validate the modeling. On the supercritical CO2, we've been running this project since 2017. This is part of the Horizon 2020 project, Scarabaeus, coordinated by Politecnico di Milano. Our focus on that is to lead the turbomachinery work package, where we are partners with, at the moment, GE Baker Hughes from Florence. So the aim of this particular work package is to look at turbomachinery designs for large power plants for concentrated solar power. We're looking at the scale of 100 megawatt plant, which means a 100 megawatt plus turbine. But also we are looking here not at pure carbon dioxide, but we're looking at carbon dioxide blends. So carbon dioxide blend is blended by small amount of dopants, and the objective of that is to raise the critical point temperature from around 30 degrees or so to just near 40 degrees. And this is to allow a condensing cycle at ambient conditions in typical solar fields. As you've seen from the previous presentation, the condensing supercritical CO2 cycle, where you can have, rather than having a compressor, you have a pump, which reduces the compression work of the cycle and hence increases the thermodynamic efficiency. So our work really is on the development primarily of the component performance and cost model and loss characterization for the large scale turbines, and these are in this case multi-stage axial turbines. We just started a new project funded by EPSSC on supercritical CO2. This is, we call it Scouter or Scooter, depending on how you pronounce this abbreviation. It's a CO2 heat recovery. So this is for industrial waste heat recovery from heavy industries producing higher temperature waste heat. But this particular technology will be well suited as well for Carnot batteries. So our objective in this particular project is to explore design innovations for a relatively small scale in the order of megawatt scale supercritical CO2 machinery. We've heard the advantage of supercritical CO2 as a working fluid, particularly the non-flammability near, for example, steel industry, where you worry about leakage and any issues if you want to recover the heat from resulting from those processes. So what we will be working on, numerical investigations, theoretical investigations, but we are building a blowdown test facility to investigate the flow at the entry of supercritical CO2 compressors, as you will see the importance of that in the next slide. So this project just started, it's going to run for 3 years. I hope we can be in the lab very soon to start building our test rig. Let's now go to the ORC turbines and see what are the challenges there. So they're typically small specific work, which means that we have large expansion ratios in a particular turbine. So it means that the turbines would have small blades at least at the entry. And we have low speed of sound of the working fluid, which leads to very high Mach numbers. Flows in certainly at the nozzle guides vanes of the turbines, but at the turbine entry, and you can see Mach numbers approaching or exceeding 2. Additionally, we have the operation being close to the critical point. And what does this imply? As you can see from the TS diagram and the compressibility, close to the critical point, you end up with significant influence of non-ideal gas properties, which mean that typical design tools that we're familiar with from ideal gas turbomachinery are unlikely to be the most suitable as they are, and you might need certain modifications or adaptation to this particular working fluid. So these combined together really would lead to unconventional turbine geometries, but also the need for validating of the design tools. Now, the ORC turbine design challenge, hence, is many design design studies are based on empirical loss correlations, derived typically for ideal gases. And there are a lot of uncertainty due to, of course, non-ideal gas effects. So ORC rigs only characterize the basic performance, which means that looking at inlet and outlet conditions, pressure ratio, efficiency, and mass flow rate. CFD, of course, is widely used at the moment as a tool for the design and analysis of those machines, but it has not been sufficiently validated because of the lack of detailed experimental data. And hence we have decided to build this test rig. It's supposed to have finished almost at the start of the lockdown, but now we are about to complete it again, having limited access to the laboratories. This is a unique test rig based on adaptation from an industrial refrigeration test rig. So it contains a twin screw compressor and a twin screw expander originally, and it operates not on a cycle, but we use the compressor to compress the flow, and then we cool it, and then we pass it through the expander. And we have added to this test rig another path to a supersonic loop where it studies the flow in the subasteric region within the nozzle guide vanes or near the entry of a compressor. This is would have a visual access, so we can have PIV measurements of the flow, which would aid in the lacking of two experimental data to validate the computational fluid dynamic models. So the test rig would operate in two modes: one mode to investigate the twin screw expanders, and one mode where we are looking at the turbo expander representation, though there's no rotational expander here. Now, in terms of supercritical CO2 compressor challenges, and sorry that the time is limited, so I have to rush through these rather than go in a lot of detail. The challenge there are high thermodynamic cycle performance requiring us to operate pretty close to the critical point. But what happens close to the critical point? You can see from the graph here, there are significant operational stability. What we see is that small changes to the temperature or pressure ratios close to the critical point, you get very sharp gradients in the fluid properties, such as, for example, here, the density and the specific heat. And these pose significant challenges to the design and analysis of turbomachinery in that close to that region. But also looking here at the compressibility parameter that I show, and as you go here to the right of this curve, you can see this parameter reduces, which means that the non-ideal gas properties become very significant. Again, that renders most of the design and analysis tool that we have for ideal gas compressors, if you like, not necessarily suitable for this type of designs. And more importantly as well, if you get very close to the critical point, and this is not our pictures from the literature, you get supersonic expansion close to the leading edge of a compressor, which you might end up with a pressure drop leading to you going into the two-phase flow region and having liquid droplets of supercritical of CO2 entering the compressor and causing all various issues when you have a turbo compressor with droplets. So these are the studies that we are focusing on the SCATTER project to have better understanding and in terms of analytic and experimental data that help us validate the model and improve the designs that we can obtain. So the supercritical CO2 as well have serious turbine design challenges. So the performance, as you can see from the chart here, of supercritical CO2 is actually more sensitive to the changes in the turbine efficiency than the compressor efficiency due to the slope of this curve. So the turbine performance is very important, and we've seen as well these machinery are much more compact than typical machinery due to the high density of the working fluid. So we need high clearance, and we end up with high clearance and windage losses observed, especially for the sub-megawatt scale machines. Technology has not been demonstrated at large scale above 10 megawatt. There are some demonstration plants at 10 megawatt or less, so it's very difficult to validate any models you develop. Hence, current designs are conservative and they rely on low pressure ratios. And then there's a fine balance here between aerodynamic, mechanical, electrical, and rotodynamic considerations, which you have seen from the previous presentation, the design of supercritical CO2 cycle. But of course, there's uncertainty in suitability of existing design models, as I repeatedly said. And a large part of our work at City is looking at the interaction of all these parameters in the design of the turbomachinery, be it a turbine or a compressor, but primarily the design of the turbine is happening within the Scarabaeus project. Of course, as well, there are a number of issues related to turbomachinery for the wide range of power generation here, from a third of a megawatt to 300 megawatt. You can see there's a wide range of potential for turbine and compressor designs, but there's significant overlap in the type of the machines or number of stages. So there is a significant need for research to have better understanding and allow us to make the right choices in the design, but also the choice of pairings, the seals have the same issues, as well as the alternator and the shaft type, whether it's a dual or a single shaft. So in going to the final, almost the final slide of this is the existing CO2 turbines types. So here looking at the existing ones, because we know that there's only a sub 10 megawatt, and you can see that there's a scatter between radial and axial turbines, and the dots show that these are actually existing turbines that either demonstrated or under demonstration. So the size of those, you can see, is very tiny. If you imagine this is for the 1 kilowatt type, but if you go for the nearly 10 kilowatt machine, you can see that these are very small and hence non-conventional, and the issues of designing those from various aspects can be very challenging. So in summary, current research in turbomachinery, particularly in relation to non-ideal gases, will likely to complement the development of Carnot batteries, because we think that the power cycles that we're looking at can be an essential part if we develop highly efficient power cycles of the Carnot batteries. And our experience in the development of both organic Rankine cycle and supercritical carbon dioxide could have a significant role in your field of research and development. There remains a significant challenges in developing suitable design tools which account for non-ideal gas effects. And of course, there is a need for dedicated test facilities. We are doing 2 of those, but there are a number of them coming around, and coordination in that front is essential, and we have significant coordination with people working on ORCs, and we're building that on organic Rankine, so on supercritical CO2. Non-ideal gas turbomachinery can be significantly different from conventional design, so we need to have that improved understanding. And the SCO2 turbomachinery, of course, require successful demonstration to enable us to validate the modeling and analysis tool that we have. So depending on the application, component development typically is a balance between multitude of parameters, which is with aerodynamic, mechanical, electrical, and rotodynamic considerations. So it's truly a multidisciplinary research. And that's it really for my presentation. So if you have any question, if you would like to contact me later, here's my contact details and my email in this last slide. Thank you.
Thank you very much for this presentation. We have a few questions both in the chat and also live. Yulong raised his hand again. Yulong, please go ahead with your question.
I have a very quick question, Abdul. So my question is a very simple, it's not technical question. Is there any sort of manufacturers of supercritical turbomachinery at the moment which produces, the components of supercritical cycles, compressors? A compressor, I know there is a man would produce that. Just the expanders, for example. So, and the same question for Emmanuel. Sorry, apologies.
Yeah, of course. At the test rig size, there is one in Brunel University which has been manufactured by a French company. That's a very small scale one. This is being tested. So this is a test rig rather than a commercial one. But we're working with the GE Baker Hughes in the work package, and they are interested in developing. They do, of course, compressors, and sometimes they call them pump pressors, really, because they do the compression in the liquid and if you like, above the critical point phase. But they are at the moment in the process of developing designs for about 25 megawatt cycle turbines, really radial inflow ones. But I don't believe they're available commercially, and they're involved in a number of projects. There are a number of other companies are entering the field from either the steam turbine side, adapting their steam turbines, or from the gas turbine side. Which one is going to be the right one is still yet to be seen.
Yeah, I can maybe comment. I can only confirm also the same from our side. So in our case, we deal with slightly lower temperature than maybe supercritical high temperature CO2 turbines, and this makes the whole mechanical design or material design little simpler. But at the end, it's modification of steam turbine technology or gas turbine technology fit for the SCO2. We need to be careful at some aspect, but at the end, it's something which is, yeah, that's engineering. It's not. It's between engineering and development, but that's not something which is out of the mind. So yeah, it's a question of cost and time. If I try to want to summarize.
Okay, Emilio, if I could sort of twist your arm to sort of predict when those turbo machinery would be on the market.
When? I would say couple of years. It depends on the project demand. I think it can take maybe 2 years, 3 years to have a kind of first standard product. Yeah.
Okay, thank you. So for small scale ones, both Emmanuel and Abdou, the small scale, let's say kilowatts or tens of kilowatts scale, are there any sort of in development or sort of already products in the market?
Yeah, there are, as told by Mr. Seymour, there is one French company which is producing this kind of SCO2. I don't know in which scale, but 100 kilowatt or 50 kilowatt in this scale.
I think around 30. I mean, the one in Brunel University is around 30 kilowatt. It's
okay.
too small.
Yeah.
We were intending to do one about 300 kilowatt in one of the projects, but we gave up on that because it was pretty difficult to find a company to do it. But these machines are very small, and everybody would be worried about the ceiling, and also if you're talking about a radial inflow turbine, so the axial thrust is enormous, and having the right bearings for that is a major headache. So one of the concepts is to design a turbine which is shrouded and just going radially out, but there's no actually. So it's just going. The flow comes in, and the blades are just radially out. It's a serious problem to design those from mechanical, from sealing, from not just from aerodynamic. And of course, the blades would be very tiny, talking about height of millimeters or less. For that scale.
Thank you very much, and that's really useful. Thank you.
Thank you for the question. We are drawing to the end, but we have 3 more minutes or so for question. I pick a couple of them from the chat to Emmanuel. Perhaps I gather a couple of them. So one is what is the expected power-to-power efficiency and the power rate you mentioned, 20 to 50 megawatt. Is it this for the electrical discharge?
Yeah, so the power-to-power efficiency is around 45% at the current stage, and yeah, the 20 to 50 megawatt, they are rather defined on the compressor side, so on the charging side, and as you see, it's more difficult to have like higher power turbine, that higher power compressor, which are actually yes available on the market, and we need to take into account this round trip efficiency of roughly 50%. So we need to choose if we want to compromise the discharge time or the power. So that's mostly a choice that we need to do. But yeah, to answer clearly the question, the 20 to 50, that's the charging power.
Thank you very much. So again, probably on the aspect of, let's say, compromising performances, another question was around the payback period time, 5 to 7 years was mentioned, and how this basically depends on the services that you intend to provide with the system. You mentioned it's quite flexible, heat, cold, electricity, but clearly that might in fact affect the economics of the system.
Well, that's a question difficult to answer in 1 minute because it depends so much on the conditions. So we did a different use case, and the best use case were maybe 2 years. The worst use case were actually no payback. So it depends on a lot of parameters, like the size, first of all, the electricity price, really the need. And all, when you put all that together, you get some numbers, and 5 to 7 years is like an average one.
Point. Absolutely, thank you. Perhaps I'll close with a question for Nasser. You mentioned quite a few times that the let's say peculiar conditions taking place in the turbo machinery you are studied leads to unconventional geometries. Can you expand a little bit more? What sort of how these geometries departs from traditional one. Perhaps this is also a very broad question, but it would be nice to hear a few words.
Let's say, for example, for an axial turbine, you end up with the blade heights are too short, which means that the tip gaps are too large in proportion to the blade height. That these machines end up with significantly high tip vortex or tip losses. So that's one example of the design that you encounter. I mentioned earlier as well, in terms of smaller machine, if you want to have a radial inflow turbine, one object is just to have the radial outlet part of it completely, and cut off the front to get rid of the challenge of axial thrust. So these are some of the aspects that will be completely unconventional. It's as well, some of them are obvious, some of them are subtle. For example, a lot of ratios. For example, you have design rules and they say you have to have blade solidity ratio, whatever recommendation to those in a certain air turbines, but you'll find these might not be suitable for supercritical CO2 turbines. So these are the some of the aspects that would be completely different. And most of the loss models or design tools have, if you like, recommended values for those that might not apply for supercritical CO2.
Okay, fantastic. So thank you very much. I think it's time to close this first day of the webinar. So I would like to obviously thank everybody, the attendees, all the speakers for the time and you committed to this workshop. I think it's been definitely very interesting, and a lot of discussion conversation can start from here. I would like to remind to everybody that obviously there is a second day for this webinar, starting again tomorrow at 9:30 UK time. Is the same link that was provided for today, and we will have also there a mixture of presentation from industry and from academia. So I would like to thank everybody. Thanks all the team behind the organization of this webinar, and we are looking forward to see you tomorrow again. Thank you very much.
Thank you very much. Thank you. See you tomorrow, guys.